can OLR be used for, apart from it's just the measured net radiation that comes out of from the Earth, essentially. And we have a spatial distribution of this. What can OLR be used for? This is a kind of a temperature, right? Can be converted into a temperature because it's the radiation. According to Planck's law, this is related to a temperature. And in particular, it turns out that this temperature will obviously be, we know this, how the structure of the atmosphere is. If the satellite can see essentially to the surface, we measure high temperature. If the temperature, if we measure low temperatures, that means it's probably cloud which radiates this out. So the OLR is a measure for kind of if there are clouds in the atmosphere or not, or at least high clouds and low clouds. It's actually used, there are very fancy inversion techniques that use the measurement of OLR to convert it into a rainfall quantity. So OLR and rainfall in the tropical regions at least is often has often a very, very good relationship. In exotropics maybe not, because many of the rainfalls in exotropics are maybe related to low clouds. Low clouds have maybe the same temperature as surface, so it may be very difficult to distinguish it. But in the tropics often high clouds are related to convective rainfall, and therefore OLR may be used as a rainfall estimator. But still, rainfall is something that, you know, so far in our waves we haven't really discussed it. So you could plot this with actually measurement of the zonal wind, for example, and I can tell you that that figure would look exactly like this, or nearly exactly like this. If you take data that are then difficult, measurements are very difficult for that quantity, but what we can use is reanalysis data, a mix between model output and measurements, the best estimate for the past, let's say 50 years. We could use that data set, daily data set of zonal wind or meridional wind, or yeah, I think those would be the best quantities to use. And we do a power spectrum analysis, we would come to a very similar outcome of that. The reason is that in the tropics there is a good connection between convection and how this convection is then propagated by the waves that are propagating. So convective events can be seen often from a satellite because things are propagated by wave propagation. That's the reason we can use this also as a proxy for our tropical waves, to understand our tropical waves. So of course what we have to do is if we have a field like OLR that can be a function of, in this case, x, y, and time, because z, there's no, this is just a field that we measure from the satellite, just the net radiation that comes out. If we want to produce such a power spectrum, we have to do a Fourier transform, and transform this as something like, that could be k, L, and frequency. But we want this representation, which goes back to what we find in our dispersion relationships, in which actually we do some kind of Fourier transform by inserting the wave number, the wave numbers, and then calculate the derivatives. So we want this kind of expression, and then we want the energy kind of that is included in this, so we have to calculate the square. And then if you do this and you subtract some kind of background spectrum, there are whole techniques to do this properly. You might find a picture like this. This picture you find if you look for a power spectrum of tropical waves. You you go on Google, you will find pictures like this. Some of them are based on OLR, some of them are based on other quantities. Often they look very similar. This can also be used, for example, you have a numerical model and you want to check if your model has all the waves that we think it should have. You can try to produce a run with your model, and if the model reproduces climate, then you should be able to produce energy in the places where we see that in observations, if your model produces anything close to what observations do. So the red color means here that the power is high, and the blue color means essentially that the color is low. So where we have red color here, we have high kind of energy in this spectrum. One very prominent wave type, probably the most energetic one, is this one here. And if it's in a frequency wave number space, it looks like linear. So it means we have non-dispersive waves. The phase velocity, c over k, is not a function of the wave number anymore, if it's a linear relationship in this diagram. So these are, we will learn today, we will derive them today. These are referred to as equatorial Kelvin waves, actually. The most powerful wave that there is in the equator, in the atmosphere, and probably also in the ocean. Ocean much slower than in the atmosphere, but so we find these waves. Then we have these other waves here, which we will also derive today, which are equatorial Rossby waves or inertial Rossby waves. It's a little bit, the theory says, therefore these lines are shown there, the theory says that they should obey a dispersion relationship that goes like this. But from this diagram, without theory, you could essentially draw any curve through this, right? Without knowing a theory behind these, you would not be able to say, oh yeah, these obey kind of maybe such a dispersion relationship which comes from theory. Whereas Kelvin wave seems to be really linear even in the observations. But here we could draw something like this or something linear also. It's very difficult. So without a background theory we would not be able to do this. And then there's these other waves here which are internal gravity waves, which are higher frequency. And there's this energy here at the bottom with very low frequencies. In wave numbers, this goes to wave number, a few wave numbers 2 to 5 or something like this. So around the zonal direction, we can observe 1, 2, 3 wave numbers. Does anybody know what this accumulation of energy here at the very low frequency band here means? What does this represent? Just launch some phenomenon, some tropical phenomenon that you have heard of that influences weather on a seasonal timescale. ENSO would be even lower frequency because it turns out that the frequencies that we have here are about this wave type is a wave type, even though it doesn't really seem, it's so slow that it doesn't really, it looks like a standing wave. It propagates around the Earth in about 90 days. Walker? It's somehow related to the Walker circulation. Have you heard about the Madden-Julian oscillation? It's relevant for ENSO actually. Madden-Julian oscillation type perturbations can lead to an ENSO events. But these are kind of, we will not look at the theory behind these because it's still under scientific debate. It's kind of a wave type that is much more complicated than the waves that we will derive today. Because we really need, in order to understand these waves, it's still debated, but it's very likely you need moisture, you need convective feedbacks. It's unclear if you need ocean feedbacks actually, but some people claim you need even the ocean. It's an ocean atmosphere feedback mechanism that makes this wave propagating. A very complicated wave type that we will not discuss here. The theory behind this, there are several theories, but I don't think there's anything very well accepted yet. But people try to propose theories for this. Instead, for these other waves, the theory is quite clear, and then we will derive this today with a much simpler model than the atmosphere, actually, which makes things simple again to interpret.
Excuse me, Professor. May I ask about, you say that the outgoing long-wave radiation in the tropics is related to rainfall.
Yes.
So, wouldn't that be a statement that is not valid, for example, for places like Congo with very thick forest and therefore low outgoing long-wave radiation, but associated to heavy rainfall?
Low outgoing long-wave radiation means heavy rainfall. This is always the case. I guess also for Congo.
But I thought if a place is covered by thick forest and vegetation like Congo.
No, because the radiation would still doesn't, forest is almost like ocean, is very dark, so that there's no differences. Even desert, in the desert it hardly rains any time anyway, but this could be measured even in the desert, because we will always have a relationship that the temperature is decreasing with height. And if we have a high cloud top, the temperature perturbation with respect to the surface would be like 40, 50 degrees. So it's a huge perturbation that we see there, that we can well distinguish from any other inhomogeneities that may be there at the surface. So it can be very well used as a proxy for tropical rainfall. In fact, if you look on the American Weather Service NOAA, it's called webpage, which give climate indicators. You can find sea surface temperature is one output that they show. Another is OLR. In OLR, when there's El Nino, for example, you can clearly see this. Shows the typical El Nino rainfall pattern that we know. So the OLR and rainfall is really, in the tropics, a very well indicator, a very good indicator for rainfall. It's not a one-to-one correspondence, but it's a very well connected feature. But you could think of, forget about it. The OLR is too complicated. You can do exactly the same thing with U-wind. With U-wind, which would be more closely related to the theory that we present now, because the waves are really in the U field, and then the U field may cause convection that then is represented by the OLR and that propagates with the waves themselves.
So I have a question about this pattern of energy next to the Kelvin waves and between the Rossby waves.
This is a minimum.
Yes.
So this is a lack of energy, actually.
It can be something like these ocean waves, but in the atmosphere, the Janai waves, because it has.
I don't know if we see them here. I'm not 100% sure.
Because I remember this is a kind of a mixture of Rossby and Kelvin waves, something like.
Sanai waves. Let me think. I've heard about them. So where you find them at the equator?
Yes, but mainly in the ocean, if I remember well. The Kelvin waves from is pushing, is going to the American and go back, because Kelvin waves can have negative number waves. So.
It could be that some of the waves we derive today have also the name Sanai waves. Okay. I'm not 100% sure that is not the case. We will have to look that up. It could be that some of the waves that we derive today are actually called Sanai waves, because in principle the derivation we do today is actually strictly valid for the ocean. So at the moment we will not be able to even to distinguish ocean and atmosphere. The final distinguishing factor is that we say, in the end, we say, okay, we get our dispersion relationships, and there's a scaling height h, and we adjust the scaling height such that the phase velocities that we get from our theory correspond to the phase velocities in the atmosphere. But if we make them corresponding to the phase velocities in the ocean, then we have recovered the ocean case. So I guess some of the waves that we derived today may be called Sinai waves, only that, I don't know. Maybe you can identify them once we are, because they're all mixed Rossby, gravity, inertia, gravity, waves, and so on. Another possibility to see these waves is this is actually from a model, and this is now taking the U-wind. This is taking the U-wind, but we do something much simpler. We have a sea surface temperature perturbation, in this case in the tropical Atlantic. Could have been Pacific, but we can say, okay, that's also in the Atlantic. There are sea surface temperature perturbations that, like the El Niño phenomenon in the Pacific, can cause perturbations to the convection. Right? You mentioned that last lecture, that we have, that brings this fantastic thing. Oh, yes. I don't know. So we discussed this. If there is a positive SST perturbation, what does it do to the convection? It increases the convection. It makes the atmosphere more unstable. It increases rainfall, convective rainfall. That is compensated, remember, by a positive vertical velocity to a first approximation in the tropics, because we have to cool off this heating in order to get into a stationary state, let's say, which is in the tropics very quickly reached. So we get rising motion that when it hits the tropopause is converted into horizontal motion. A part of that would be zonal motion. This is what we kind of see in this Hofmüller diagram. This is now just the u component of the velocity, so that what we would see here, over the SST perturbation, and this goes now to the east and to the west. This is shown here. We call this Hofmüller diagram, and this is time. So at time 0 in the model, switch on, there was no convection anomaly with respect to some control simulation. But then the convection sets on and causes this perturbations in the U-wind. So we see that on the eastern side of this perturbation, as expected, we get positive U-wind, and on the western side of the perturbation, as expected, we get negative wind. It has to, because of continuity, no? The air that rises here has to flow in this and in this direction. So this is not a big surprise. What can we learn from this is actually, what you can derive, is the phase velocity. And they are not the same. There could be several hypotheses why they are different on this side and on this side. One is there is some kind of mean flow that changes, it causes a Doppler shift. But in reality, it turns out these are different wave types. This turns out to be again the Kelvin wave that propagates, we have seen in the phase diagram, propagates eastward. There's a positive relationship here. And this is the equatorial Rossby wave that propagates westward. And they have different dispersion relationships and different phase velocities, therefore. So these are much slower than this. So this is important, of course, because the information is transported very quickly to one side and much slower to the other side. It's an interesting feature. So this could be relevant for these kind of analysis. So we will use, to derive these waves, we will use the shallow water equations again. The same equations we have used for the extratropical waves, as long as they were stable. When we looked for baroclinic instability, we had to use a different set of equations that has the thermodynamic equation included. But for the pure barotropic Rossby waves, we were happy even to use the shallow water equations. So this is just a summary again what the shallow water equations are. We have discussed this already. We don't have to spend much time on this. And then this shows the proper derivation of the shallow water equations. But you know this already. All of this you know. You can just repeat it to remind yourself what it was. So we take the two horizontal momentum equations, the hydrostatic equation and the continuity equation. And this becomes trivial because if the density is constant, this is just a divergence-free, incompressible equation. We can integrate the hydrostatic equation. We can replace the pressure gradient by the height gradient of our system. And finally, we can integrate the incompressibility condition to get an equation for the height of our system. So whenever there's convergence, the height has to go up. It's a one-to-one relationship. So this equation is now a complete set of equations that we have used already before to calculate, for example, in the exotropics, our inertia gravity waves and Rossby waves if we apply the rotation to the momentum equation. Now comes the difference. We now say, okay, different from the exotropics, we let our base point be now on the equator. On the equator, it turns out that if we do a Taylor series expansion of the Coriolis parameter, the F0 on the equator is exactly 0. Therefore, the first term that remains is beta y. So instead of F0, which we had for our extratropical perturbations, now we have beta y standing here. Otherwise, the linearization of the equation that we have just seen is exactly the one that we did on the blackboard, having zero mean flow. And that implies that the mean height is not zero, is constant. And that fulfills the set of equations. And then if you look back our lecture, we have derived that this is the set of equations that fulfills this. Then the first order perturbations equations after linearization. The difference is, instead of an F0 here, we have beta y. And that causes a problem. The equation looks quite simple, but it is not that simple anymore. See, this is a small complication, but it already, is a linear equation. The problem is the coefficients are not constant anymore, which makes the solution already much more complicated compared to what we had previously. Okay. So note that we have set the basic state to be constant. We could use a u velocity that is different from 0, that essentially, if I remember correctly, would just lead mostly to a Doppler shift of your solutions. So all solutions would be very similar, but would have some kind of Doppler shift. But it's common practice to first say, okay, in the tropics, the mean flow is much less important than in the exotropics. Definitely true, always true for the ocean. But for the atmosphere, could be a good setting. But even we wouldn't know, depends where we are, if our mean flow on the equator is actually westerly or easterly. It can vary from place to place. So it's not that clear. So this is our set of equations. Regarding the scale height, HE, that we have put here, for the time being, we could say, of course, what would we say? It's the height of the tropopause. It turns out if we set this to the height of the tropopause, the final phase speeds that we get are completely unrealistic. They are not the ones that are observed. So this scale height is different from the height of the tropopause. For the ocean, it turns out we can, of course, take not the depths of the ocean actually, but eventually we can, if we apply this, in the next lecture we will apply this to the ocean case, what we can use is the depths of the thermocline, what is called thermocline. And then this represents the real observable quantity. But for the atmosphere, that's not the case. There are ways to derive, of course, the proper set of equations. But now we say we keep it as simple as possible and use this incompressible shallow water equations and see if the solutions look like anything what we have observed. And if they do, we can be happy. We have understood something with a still quite simple derivation, which is already complicated. The real compressible system would be much more complicated, and we would have much more trouble to solve it analytically. At least me. So we can now search for such solutions. But due to this problem that is a system with non-constant coefficients, actually one trick that we can try to use is to say, okay, there's no easy theory now how to use this, but one trick that we could try is to separate the dependence of x and time from the dependence of y. This means that those waves would not propagate in meridianal direction, but would have some kind of structure in the meridianal direction, but propagate only in x, in zonal direction. So they have a fixed structure, can be any, right now could be anything. It turns out they have to decay as we go away from the equator. That is already clear. But we will come back to that condition several times again. But it's already clear that we cannot go too far away from the equator, because then this approximation breaks down at some point. It's not a good approximation anymore to the original equations. So maybe we can go 20, 30 degrees, but not more. So we want to look for solutions that look like this. You kind of dream this. Is one of the tricks that is used in math to solve an equation with non-constant coefficients, to say that, oh, the dependence from y is separated from the dependence from x and t. And then you try, is this a solution or not? You just insert. And if it fulfills the equation under some conditions, then you have found a solution. You can simply try. And if you try, it's very simple. You will find this is the set of equations after inserting these perturbations, dividing by the exponential, and eliminating as much as possible everything else. But this is just dividing by the exponential, because we cannot divide anymore in this case by the amplitudes. Now these amplitudes here, u hat, v hat, and phi hat, are functions of y. They are not constant coefficients anymore, but they are functions of y. It's quite straightforward now to manipulate this equation. You can insert, derive this equation from that and insert it in the other two equations, and then you eliminate the u component. It's just straightforward, basic math. And then you can again say, okay, I eliminate from these two. This is an equation now for v hat and phi hat, so I eliminate phi to get just one equation. You can do this. But note that here, at that point, this comes back later, by doing this, we divide here by this term here. So we assume that this cannot be 0. This has to be different from 0 if we insert this there. And then we get this equation here. So we kind of remove here a gravity wave solution by doing this. So this is the final equation that we get for the original perturbation of the velocity. But it's now a partial differential equation in y direction. If this term was 0, then it's just a simple equation to be used, a simple quadratic equation to be solved. Would give exponential solutions. But we have this y dependence here. Now, it's not that I have found this, but mathematicians have found that this can only have solutions that decay away from the equator if this constant factor here is not just any number, but has to be an odd number, with n being some kind of the meridianal wave number of what we of the waves that we define later. So n can here be 0, 1, 2, and so on. Then this has a solution, has solutions that decay away from the equator. And this is already one part of our dispersion relationship, because this, as you can see, gives us a relationship between frequency and wave number already. If you can reformulate this by just a rescaling of the original y distance here from the equator by something that we call psi, which is dimensionless, scaled by this factor. It's just a trick. And then it turns out you can reformulate this equation in this form here. And sometimes people like to do this because this equation is actually known. This equation is a known equation in this new variable, in the scaled meridional distance psi. And it's an equation for the differential equation for a quantum mechanical harmonic oscillator. Not that I have studied that very much, or at least I don't remember anymore. It's too long time ago. But yeah, that's the case. So, but that's the good news, because that means people have studied this equation so much that we can trust their solutions. Yes.
Excuse me, but may I ask about the format that we have used? Because from the beta planar approximation, we assume that the perturbation, which is represented as the beta parameter, is relatively small compared to the f naught. The beta naught y is relatively small compared to f naught. In this case,
so okay. This is what we have always used as first kind of a Taylor series expansion of our Coriolis parameter in terms of the constant value and the first order perturbation. Okay? And in the exotropics, we have said whenever they appear together, f naught is much larger than beta y. That's true for the exotropics. But in the tropics, that breaks down, because f naught is exactly 0. And then the only term that survives is the beta y, plus higher order terms. But we assume, okay, they are small again. That makes a difference, essentially. So on the equator, the mean Coriolis parameter is 0. It can be a problem for many of the things, because sometimes you divide by, in some of it could be convenient to define a geostrophic wind. We have divided by f. But if f is 0, of course at the equator we cannot define a geostrophic wind. So it can cause sometimes trouble. We will have this problem later on. So there's actually some kind of problem here. But at the moment it's not a problem for us. It just makes our set of equations different. Of course, in reality, even in the exotropics, we had this. Only that it was a sufficiently good approximation to say, okay, this is so small that we can treat this f as if we don't go too far away from our base point, as a constant. But at the equator there is no way we can do this, because f naught is 0. So we get a different set of equations, fundamentally different, which at the beginning looks quite simple, but eventually it turns out to be quite nasty, because we have to use already some kind of complicated theory to solve it. So what they have found in that theory is that actually what solve these equations are what is called Hermite polynomials, which can be expressed as the solution would then be this Hermite polynomials. N is the number that corresponds to this number here, and they are all these then are forced to exponentially decay away from the equator, because y is proportional to the psi here. So they all go as a Gaussian, but they have some other structures, some more complicated structures, depending on what wave numbers we use. Actually, if we insert this into this, then that is the defining for every n. That's the defining equation for this Hermite polynomials, and you can do this actually if you set n equal to 1 here, and you insert this there. It's very easy to solve then. Oh, the first Hermite polynomial has to be 1. Then you insert, or the 0 in that case, it's actually for 0. For 1, then it turns out the solution of this becomes if this Hermite polynomial is 2 times psi, and so on. So these correspond, then this n corresponds to the nodes we have in our meridianal domain, essentially. So the first one is just the Gaussian distribution, something that is maximum at the equator and then decays away. The higher ones, they have, for example, this one has a node on the equator itself, then grows and decays again, and so on. So we don't have to worry about this. Other people have shown that this is a solution of this equation, and we can be happy. So we want to consider the case n equal to 0, where we have the Gaussian distribution separately. And it turns out to be an interesting case. For that case, for n equal to 0, one can write this in this equation here in a different way. You can show that it is actually easy then to factorize. You can show, okay, that expression there is equal to this times this. That has always the advantage that you have found already solutions, because one solution is this, the other solution is this. So one solution here would be a gravity wave, and the other solution is a mixed kind of Rossby gravity wave kind of thing. So this solution here corresponds to a westward propagating gravity wave. But this is actually not permitted, because when you derive that equation, we have divided by this term here. So there was some kind of problem here. But for the other root here, we can find the solution. It's just the quadratic equation. I'm just wondering if it's because it's a quadratic equation for nu. Okay, so you get this expression here, already quite complicated. And you can see this is in generally something that we call mixed Rossby gravity wave, because both the beta parameter, which indicates this is a Rossby wave, plays a role, and this gravity parameter, which is square root of gh, plays a role. So therefore they are called kind of mixed Rossby gravity wave. It's kind of interesting to do a very small, simple calculation for the case where k is actually large enough. So k large means large wave numbers, so relatively short waves. Looking for this for a relatively short wave solution. Then we have, okay, something like nu equal to k square root of t times ph 1/2 plus or minus 1/2 1 plus, and I call this x, and we take the square root of this. So this number here, 4 beta over k square he is called x. So we consider cases for large wave numbers, small wavelengths, where x is small. If x is small, you find that 1 plus x square root of that is about 1 plus 1/2 x. And now we want to look for the solution for the Rossby wave type solution that propagates to the west. So we consider this sign here. Otherwise, this okay. These are the dominant terms, and this is just a gravity wave. So if that's the case, and we take the negative sign here, then the 1 goes out. This goes out with this, and what we get is nu equal k square root of he minus 1/4 of x times. So x is now, we replace this here. X is 4 beta over k square root of gh e. So this minus. So this becomes minus. This goes out. 1 goes out here. The 4 goes out. Beta over k. Or c equals minus beta over k squared. That's a Rossby wave. So we get for large wave numbers, small, relatively short waves, we get back an equatorial Rossby wave as an approximation to this equation here for one of the two solutions. The other one remain always mixed inertial gravity wave. But this, the approximate version of this looks like really a Rossby wave that propagates to the west. But yes.
What is the typical length scale with which we compare the wavelength?
It's a good question. It probably depends on what causes your waves. So for the atmosphere, I think 1,000 kilometer would always be a good guess for wave length. And then that would be relatively short waves, so they would fulfill this. Long waves would be really 10,000s of kilometers or something like this. Wave number. So yes. So 1,000 kilometer waves, so relatively large wave numbers. So in a zonal domain, you can fit probably more than 10 of them, 10, 15, 20 probably. Then that would fulfill that criterion. Yes, but it's a very good question. We've seen for the MGO, the wave numbers would have been 2 or 3, so very, very long waves. But for Kelvin waves, the wave number can be anything, but well, we can look at our diagram. Maybe anything actually. Wave numbers between 2 going up to wave numbers 10. So there could be all kind of for the Kelvin wave, okay. For the Rossby waves, oh, Rossby waves are actually here. So could also be 5 up to 10 or something like this. Depending on what kind of phenomenon they are due to, which could be some kind of random convective events or other perturbations. Okay, so there is now one very special case, which is the equatorial Kelvin wave. And it's a new solution that can be derived, and we do this ad hoc. We say it is found, we find in observations or from experience that an important wave type obeys the criterion that the meridional velocity component is exactly 0. And that gives a solution actually. The condition that we can just pose that the meridional velocity component is exactly 0. If we go back to our original perturbation equation, that cancels out this term, that cancels out this term, and that cancels out this term. So we remain with a simpler set of equations now. Which is just this. So if you eliminate now the phi field between this equation and this equation, you insert this here, then you can see already, okay, that must fulfill a gravity wave. So we get c square is equal, of course, to nu over k square, and that has to be g over h. That's a gravity wave. But if we, on the other hand, if we insert 161 into 162, so for the distribution, we eliminate again phi here, so we resolve this for phi, insert that there, then we get an equation for u, for our distribution in the meridional direction. That looks like this. And that, of course, we know the solution. This we can know the solution, or you can dream the solution and insert. So if you dream this solution with a constant amplitude here, you insert that there, you find, okay, du by dy would be the exponential, you get that down, you derive the exponential again, and that fulfills exactly this equation. Very easy to show. But that excludes something, because if this is the solution of this, then that means that a decaying wave, a decaying Kelvin wave from the equator, can only exist if the phase velocity is positive, so in eastward direction. Because if it's negative, then this grows exponentially from the equator, which should not be the case according to our theory, because we know that the theory breaks down in that case. So we can only allow solutions for C positive. And these are our Kelvin waves. Kelvin waves are gravity waves which are on the equator and only propagate in the positive direction. The other propagation direction was excluded. The other propagation direction is Rossby waves. And as you can see, some are observations, this and this, confirm this. We find the Kelvin wave energy, if we want to interpret this as being this part, is only on this side of the diagram. We don't find any equivalent thing here. On that side we find this, if we interpret well, the equatorial Rossby gravity waves. It's good to get used to this if you look at equatorial wave propagation. Kelvin waves always moving in that direction, Rossby waves always in the western direction. Now we do something else. You can show that the E folding time, so the distance needed for the exponential to be only 1/3 of its initial amplitude is this number here. If you insert that, if you insert this, should be equal to 1/E times the initial perturbation. You find that this is the E folding distance. And now we do a trick. We say, okay, we could try to insert, of course, in order to derive the phase velocity, we could insert the height here. We will do this in a minute. But if we take observed phase velocities of Kelvin waves derived from our phase diagrams, we get that they are around 30 meters per second. So this gives us an E folding distance of 1,600 kilometers. So we can, once we are 1,600 or 2,000 kilometers away from the equator, these waves have already very small amplitude. And for the ocean, since C is much smaller, that distance would be much smaller. So in the ocean, those waves would decay very quickly away from the equator, if you want to make this comparison. Of course, we find that these Kelvin waves have the phase speed. And if we insert the height of the tropopause, as we did, this is already what we did for our extratropical case, then we get to 300. That would give us 300 meters per second, which is not the observed phase velocity of Kelvin waves. So what the scale height now means, which is if you put C equal to 30 meters per second, then you square this. So 900 divided by 10, so about 100 meters would be the height here. What's the meaning of this? Don't ask me. If it was, let's say, okay, later we will see that there are actually many flaws in assuming this barotropic structure, of course, in the tropics. In the tropics, while in the extratropics, a barotropic structure, which means that our wave type is essentially the same with height. In the tropics, waves are typically very baroclinic. Means that if there's a surface, at the surface a low pressure, at high levels there's a high pressure. So they really completely change sign with height, typically in the tropics. That could tell us, of course, okay, if we want to have kind of the same type of perturbations, we should take maybe half of the extension of our, but even that doesn't lead me to any reasonable propagation speed. So 100 meters, what this number means, I have no idea. But that's the limit of the theory, I think. These are just, it could be an exercise that you go ahead now and program the solutions. And if you do that in a domain, if you program the linear solutions in a domain, you would come up with this picture for Kelvin waves and this picture for the Rossby gravity waves. Those propagate in that direction, these propagate in that direction. We can actually understand why, for the Kelvin wave, we can easily understand why they propagate in that direction. Because if we are here, these are lines of constant height field, which is proportional also to the pressure, of course, in the medium. So we are here, assume we are here. And at that, here we have a divergence. So the flow is going away. That means the height locally should decay. that can be done if this perturbation goes in that direction. Do you see that? It's one way to fulfill this. So if we are now here locally, we find that there's a local divergence. If there's a local divergence, that means our height field should decay, should become smaller. That can be done if the wave is propagating over. And that's what the wave is doing. So the wave is propagating in the direction to fulfilling this constraint. Same is true, would be true here, where we have convergence, and then you would come to the conclusion, okay, that the height should be moving over there. So that can be taken as a...
Sorry, what is on the x-axis there?
Or just the wave numbers in terms of pi. So this would be, as you can see, the whole wave is just 2 pi. This is just an idealized case.
Normalized.
Yes. And if we look at now as a very idealized diagram, then we find our lines again that we have seen in the OLR diagram. So for the Rossby gravity waves, equatorial they are here, and for the Kelvin waves they are here. Always depending on which kind of phase speed you have. You see, the phase speed is actually, in the theory, okay, one could have one phase speed. But even in reality, we see that perhaps the phase speed is not a fixed number necessarily. There's one, no, this is probably the most likely one that we can derive from this, but kind of we find this possible spectrum of phase speeds. So the phase speed actually can be changed by several things. If you look at them in reality, of course they don't obey exactly the equations that we have used. A real Kelvin wave may be influenced by the fact that there could be the Doppler shift that we have talked initially about. So there could be a mean flow in the region where you derive them, and then that mean flow could have the effect of a Doppler shift, so you would have a different phase speed. One possibility, larger phase speed. Another possibility is that people discuss in the literature is convectively coupled Kelvin wave. Of course, from this picture we know they have to be convectively coupled, otherwise we cannot measure them in OLR. That means that these waves, they have a convection going with them. We can see them not only in the wind field, like our theory, but we can see them in the OLR, which is a proxy for convection, clouds, proxy for clouds and convection. That means that the real equations responsible for them may be much more complicated than our simple equations that we have used. We may have to take into account convective heating even in the case of Kelvin wave. And it is thought that this kind of reduces the phase speed of Kelvin waves compared to the theory. Yes, and we will not discuss, as I mentioned, this MJO type of waves. Although it's quite interesting to look at the feature, but we will not do this in this course. It actually turns out that they are, as I mentioned, very slowly propagating waves. So for example, in one phase, you have the whole Indian Ocean covered with increased convective activity, and maybe the whole Western Pacific covered with decreased convective activity. And maybe in Africa, again, another signal of this activity. And then this whole wave moves over. But if you look at the detailed structure, you will find that is propagating very slowly. But if you look at wind in the upper troposphere, you will find that this convection induces Kelvin waves, which actually escape from this MJO. And you find them already at the end of the Pacific why the wave is still there, you already find the Kelvin waves on the other side of the basin, essentially. So there's quite an interesting interaction even going on between these waves. So within one of these waves, you will find a lot of Kelvin waves and also equatorial Rossby waves generated by those kind of events. Now in the next lecture, we will make use of this theory, modify this theory here and there, apply it to the atmosphere and apply it to the ocean, and see how we can learn something about the ENSO phenomenon from that. We want to discuss how an ENSO phenomenon in the Pacific, we think first of all in the Pacific, but equivalent phenomena could also be going on in the Atlantic. In the Indian Ocean, not very much, but in the Atlantic, because it's a closed basin again. So we want to understand what kind of positive feedback mechanisms there may be going on between the ocean and the atmosphere, given this kind of theory, the wave theory that we have learned today. Actually, there we will look for stationary solutions. Here we have looked for the propagating solutions, free solutions. In the case for ENSO, we will look for what we call it's a forced stationary solution. So we will have a forcing term, which for the atmosphere we think of some kind of heating, ENSO-induced heating. That's a forcing term. Then we also have to consider a damping term, which would be just Rayleigh damping of all the velocities. And for the ocean, we think about it in a very similar way. We have also a forcing term. There, the forcing term will be the wind stress at the surface. So we have again a forcing for our Kelvin waves, which is wind stress at the surface, and damping term, which is again just a Rayleigh damping in that case, very simple friction assumption for our velocities. And then we look for stationary solutions. How do they interact with each other? How can the waves, Kelvin and all the other equatorial waves in the equator, at the equator, explain why there should be a positive feedback between atmospheric response and ocean response when we consider the ENSO phenomenon. Okay, again, no homework today. And in the next lecture, there will be a homework.